Everybody, I'm Giacomo Falcucci from the University of Rome Tor Vergata, and today we start our last session of the DSFD2021 with the plenary talk by Dr. Emanuela Zaccarelli, Modeling Microgels in Computer Simulation. Emanuela Zaccarelli is a senior researcher at the Institute of Complex Systems of the National Research Council of Italy. Please, Emanuela, you have 40 minutes. I would like 35 minutes for your talk and 5 to 10 minutes for the questions, if it is fine for you. The floor is yours. Thank you very much.
So thank you for the introduction and for the kind invitation to give us the opportunity to tell you a little bit what we are doing now in Rome about modeling microgels. So you may not be too familiar with microgels, so let me start by motivating the talk. So what are microgels? Why are they interesting? So microgels are colloids that are made by cross-linked polymer networks. And on this representation, in which basically colloidal particles are categorized, are classified in terms of their softness, that is defined as the ratio between the elastic free energy and the thermal energy. We have basically a wide variety of particles of different softness, from simple polymer chains up to hard sphere, which are the upper limit, of course. And microgels are here in between, so they have a moderate softness, which can be tuned by tuning the internal architecture of the particle. And one of the important characteristics is that they are entirely polymeric, so they are made entirely of polymer. Of course, you can tune the synthesis, adding a core, for example, having core shell and these kind of things, but we are interested in the pure network today. And they are very much interested in physics because they now represent the soft colloids, now represent the new prototype of soft matter, more than hard spheres, which have been the reference model in soft matter for a long time. So if we compare how the phase diagram of hard spheres compared to this soft particle, and in particular to microgels, with respect to the effective volume fraction, that usually these particles are athermal, the temperature in principle, if you are in a particular condition, does not play any role, you vary the packing fraction, and what you see the emergence of fluid, crystal, glass, and jamming transition at high density, and you've heard for example, the talk of George in the first day about this limit. So this is a very, very interesting aspect that is studied theoretically. And with soft particles, so what happens, what is the new physics is the fact that you don't have this upper boundary of, for example, 74% or 64% for random cross packing, beyond which you cannot pack particles, because this particle can deform, can shrink, can do things because they are fluffy, polymeric. And so you can basically explore a wide region of dense states, and you can even exceed the packing fraction 1. And so you will have plenty of overlaps or interpenetration or shrinking or deformation. So it's very interesting also from the rheological point of view to study the dense system, the dense states probed by these soft colloids. One important aspect of microgels is the fact that they are, can be made responsive. So, for example, the usual case that is studied is microgels made entirely of NIPAM, that is a thermoresponsive polymer, which, if you take a polymer chain, undergo a coil to globule transition at a temperature close to 32 degrees. And this translates at the colloidal scale in the so-called volume phase transition, in which you have a particle, a microgel particle that has an hydrodynamic radius. Usually this is a light scattering plot, for example. You estimate the hydrodynamic radius at low temperature, in this case of order of some hundred of nanometers. And what happens is that the particle shrinks up to a collapse state at the same transition that basically this is an echo of the transition of the polymer itself. And the interesting thing is that this transition is completely reversible, so you can go up and down in temperature, changing the size. And so you can probe, for example, in situ, the tuning of particle volume fraction by a tiny change of temperature, which makes it very appealing for fundamental physics, because, for example, you can study, for example, crystallization glass by a small tuning of temperature. Of course, you can change the constituent polymers, adding, for example, ionic monomers and so on, and so you can make it also responsive to pH or to other things. But for the moment, let's stick with the thermoresponsive polymer, because these are also the ones that are more used for a wide variety of technological applications, because they can be used as sensors, drug delivery objects, because they are swollen and empty, and so on. So the other important aspect for physicists is that microgels are relatively easy to synthesize, even though the synthesis is a little bit complicated. We will see a little bit later, but there is a well-defined recipe, and today is now basically they are produced in most physics labs. But when you change the temperature, what happens is that you are also changing the interactions between the particles, because as I said, the polymer goes from coil to globule, and what happens at the molecular scale is that basically the polymer likes to be in the water at low temperature and then starts to dislike it, so becomes more and more hydrophobic at high temperature. So it means that when you concentrate, for example, the microgels, you will start to experience attractive interactions at high temperature, while they are much more stable at low temperature and they are more repulsive particles. And so you will have a phase diagram that is very, very much incomplete still, if you plot it with the temperature axis now, and not only the volume fraction one. And there are a lot of aspects that need to be understood, and also what happens at very high density, as I told you before, where, for example, entanglements, physical entanglements could also play a role in attractive, as was postulated, for example, in this publication. So the point is that if we want to model this from computer simulation, we need a multi-scale approach in which we combine the relevant polymeric aspects at the colloidal scale in order to arrive at a meaningful coarse-grained description that could take into account in concentrated suspension all these effects, the shrinking, the faceting, and these kind of things that could happen. And so what we are trying to do in Rome is to build a monomer resolved, so work with some kind of coarse-grained model in between that retains some of the important aspect of the interaction with the solvent and of the fact that these particles are responsive. So before we started this program, basically microgels were usually studied as regular networks, because this was the easiest thing to do. So basically you build a regular network of a given lattice, and you put polymers chains all of the same lengths, and then you have a network, but you miss a lot of essential ingredients if you want to compare with experiments, in particular the fact that there are no entanglements, and that these are completely homogeneous, and they don't have the so-called core corona structure of the microgel that I will tell you in a minute. Why there is a core corona structure? What does it mean? It means that when they do the chemical synthesis, they have a specific protocol that they follow, which is very, very complicated for us as physicists to be able to reproduce. So we cannot hope to be able to do this in a simulation, because there are too many parameters that are involved, and there is different kinetics of the different ingredients that the chemists use. And in particular, the crosslinkers that are this other species that is added on with the monomer in the start of the precipitation polymerization, they react much faster. And so what happens is that they concentrate much in the center of the particle, leaving a more fluffy corona at the end. So this is the only ingredient that we try to retain. And then we ignore all this complicated multi-step process, and the approach that we want to follow is a more physicist approach, in which we ignore what happens in between. We just care of what is the final result and the properties of the final particle. So we want to assemble a microgel that is disordered, has entanglement, has a good corona structure, and that will look like the one that is used in experiments. So how do we do that? We do that with this monomer resolved method, in which basically we take our basically the ingredient of the polymerization, that are the crosslinkers, these red molecules, and the NIPAM, the monomers. the blue ones, and we basically replace them with a binary mixture of patchy particles. So patchy particles are colloids, spherical colloids, which have specific patches that are attractive. And so we mimic the monomers with 2 patches, so that they can just grow into chains. And we mimic the cross-linkers as particles with 4 patches, so that they can bind to 4 different monomers. And what we do is simple. We make them assemble in a sphere of radius z, and this radius of the sphere changing it will change the internal density, so the entanglement as well of this network. And we use some trick to let it assemble at low temperature to this attractive patchy interaction until we reach a fully bonded configuration. So we put a given number of monomers and cross-linkers, and at the end, basically 99.9% of these bonds that can be made are formed. And once we have that, we have a network that is disordered, is unique, and is the result of an assembly process between reversible interaction. So at this point, we do a second step, and we freeze the bonds in the sense that we replace the patchy attractive interaction with polymer ones. So namely, we use the standard bead spring model. So first, we have to do this in 2 steps. And the bead spring model is the usual model in which you have the WCA potential between the monomers, and plus between all of them, and then plus you have the Fene potential that basically prevents breaking of the bonds and avoids also unphysical crossing of the chain. So when we do this assembly protocol, we have 2 parameters in the synthesis. I call it the in silico synthesis. We have the cross-linker concentration, so how many cross-linkers we put, and we have this radius of the confining sphere that tunes the internal density. And so tuning these 2 parameters, we can obtain networks of different configuration, more fluffy, more anisotropic, more compact, smaller, and so on. And then we are interested, as I told you, in the swelling behavior. So to mimic this volume phase transition, and to mimic that, we just use, for the moment, implicit solvent. So we treat it implicitly, and we mimic the monomer solvent, basically decrease the repulsion as increase the temperature as a solvophobic attraction, as usually done in polymer physics. We took inspiration from this work. And this is just an attractive potential that acts between all monomers that is modulated by a parameter alpha, that is the depth of this potential, that plays the role of an effective temperature. And so when you change alpha from 0 to a large value, what you observe is just simply the microgel, of course, collapse. And if you plot the swelling curve, similarly to the previous curve that I showed you in the first slide, you have that here we plot the radius of gyration of the microgel normalized by the one at maximum, so at alpha equals 0, that is the maximally swollen value. And here we vary the radius of the sphere. You could vary also the cross-linker concentration, there would be not much difference. What you can tune how much the particles shrink. Of course, the less density is, the more it will shrink. And interestingly, all the curves have an inflection point at a given temperature, that is alpha equal 0.6, that is the analog of the 32 degrees in the experiments. However, if we want to compare with experiments, we have a problem. I told you that we need to have a core corona structure. And so far, I told you something that we put this patchy particle in a sphere and they just assemble. And so what you will get a density profile of the monomer within the microgel as a function of the distance from the center of mass that will be mostly flat and then rapidly decaying. And for example, imagine that you make a microgel of 5,000 monomers. You will have some core and some decay, then you increase it. This will be larger, this will be larger, and so on. So it will be not robust to size effects. And so what we do is that we add a force that acts only on the cross-linkers and try to concentrate them in the middle in order to tune this core corona structure. And we adopted a trial and error approach in which we tried different shapes of this force in order to match the experiments, as I will show you in a minute. And as a result, the final density profile that we obtain is now flat in a smaller region, that is the core, which decays much less sharply now. Instead, if we look at the crosslinker profile, now we have that the crosslinker here at high density at the periphery of the microgel are practically absent, and they increase towards the center. And this seems to be the right structure. How do we check that this is the right structure? We compare with the small angle scattering experiments, in which they measure the internal structure of the microgel, for example, by neutron or X-ray scattering. And in the simulation, we just calculate from the configuration this form factor that typically has a shape like that. So we were lucky enough to work with the group of Peter Schuttenberger in Lund, who provided us with the form factor from small angle X-ray scattering at many temperatures across the volume phase transition for a 5% microgel. And these are the crosslinker, these are the form factors which becomes more and more peaks appearing. So we compute it from the simulation, and what we do is we then match the first peak position. The first peak position will give us the natural length of the simulation, and the unit length of the simulation is usually the monomer size. And to make this comparison, we use a very, very large microgel, so that the bead size amounts to about 4 nanometer, which is still rather large. And in fact, we start to see deviation between the simulation, the lines, and the experiments, the symbols at IQ, because we cannot really probe the small distances. However, we can capture the whole decay at the beginning and the 3 peaks and the subsequent position of the peaks. And then we add the alpha potential, and with a linear relation between alpha and temperature, we can basically reproduce the form factors for all the temperatures. So this comes because we've used the right designing force on the crosslinker, we have the right core corona structure, and we have tested that this works, whatever, we did this for a very extremely large size, but if we use much smaller microgels, the agreement is still satisfactory with the same linear relation between alpha and temperature. And then recently we also, they perform more experiments, and we also compare with smaller crosslinker concentration microgels, and the agreement is still quite good. And so basically this tells us that we have a protocol basically to model this microgel that is reliable. So once we were able to do the single particle, we now are interested to see how the microgels interact. And usually people, so from the hard sphere potential for hard colloids, then people say, okay, then soft colloid just behave as soft sphere with some kind of repulsion. And for microgel, the usual potential that people use is the Hertzian potential. That is the potential that is derived between 2 elastic spheres at small deformation. And the Hertzian potential, this is just for microgel in the swollen regime. Sorry, I forgot to say. This Hertzian potential basically depends on a particular length, that is basically when the 2 microgels start to come into contact, that is a sort of the hydrodynamic radius. And then has a prefactor that depends not only on this length, but also on the elastic properties of the particle. So on the Young modulus and the Poisson ratio. And we have two moduli that we need to evaluate the Hertzian model. So what we would like to do is the following. We want to test rigorously the Hertzian model. So we take our microgel, and for it only, we calculate the elastic moduli. And then we calculate separately between 2 microgels the effective potential. And then we want to see whether the Hertzian model works, because this is the assumption that is usually made for describing microgel at dense states. So we need to evaluate the elastic moduli. How do we do that? So we started to think about this problem, and we immediately thought that the bulk modulus is very easy to compute, because it's just the inverse of the isothermal compressibility. So you need to just evaluate the volume fluctuation. And so the first problem we tackled was how we calculate the volume of the microgel. There are many ways. One way that we decided to work with is that we take an equilibrium configuration of the microgel. We take the convex hull. And from the convex hull, we determine the gyration tensor that we diagonalize, and we then take an equivalent ellipsoid that is the instantaneous, that gives us the volume of the instantaneous configuration of the microgel. And even though the microgel is almost spherical, it will be only, I mean, it will never be perfectly spherical. So instantaneously, the volume is of that of an ellipsoid. So for this, we have a way to quantify the volume. We can calculate the fluctuation and evaluate the bulk modulus that we also can evaluate from isotropic compression. But in this way, we have just one moduli. Instead, we would like to have two to compare to the Hertzian model. And so we would like to calculate at least two of them. And so, but this idea of the volume fluctuation gave us the inspiration to develop a method to calculate the elastic moduli of the microgel, all of them. And the idea is that we evaluate shape and volume fluctuations. And we do this by using elasticity theory. So we calculate the Green-Lagrange strain tensor of our microgel, that is defined like this, in terms of the deformation gradient tensor, defined like this, with respect to a reference configuration that is stress-free. And so we tried a bit, and then we decided to use the average ellipsoid, basically, as our stress-free reference configuration of a given equilibrium trajectory. And so for each configuration, then we calculate the instantaneous ellipsoid, we diagonalize, so as I said before, then we have the average, and from the average, we have this, we can calculate the deformation gradient tensor, which takes this form. So here you have the average, here you have the instantaneous semi-axis of the ellipsoid. With this, you can calculate the matrix, the Green-Lagrange strain tensor, and then in elasticity theory, it is well known that there are key strain invariants of this tensor that are called J. I mean, we call J I1 and I2, and J is related to the volume change, so it will be related to the bulk modulus, while I1 and I2 are related to the shape change of the microgel at fixed volume. So this method is generic. Now we are applying it to microgel. So what we do is that we take an equilibrium trajectory of molecular dynamics, we calculate J, I1, and I2 and their probability, and then we use a phenomenological theory like the Mooney-Rivlin one that is usually used in elasticity theory, which writes the elastic energy as a reference term plus contribution due to the three strain invariants. And the three, so this you can evaluate as potential of mean force of the probability. And the Mooney-Rivlin theory in particular tells you that these terms of the energy are quadratic for J and linear for I1 and I2 that actually appear to be identical in our case. And so within the theory, you have a way to relate basically these terms to the moduli, because W of J is simply the volume times K divided by 2, J minus 1 squared, and so on. And so basically fitting this data from the simulation, the prefactors will give you K and G, so the bulk and the shear modulus. So in a single trajectory, doing this approach, we calculate two moduli, and then using the linear relation, the relation between the other moduli, we get also the Young modulus and the Poisson ratio. And so this is a very general method that works for any polymeric system, or also could be thought to be applied for other systems. And we can calculate all the elastic constants. And so to check that this was correct, we first compare to the volume fluctuation only directly, and to the isotropic compression for the bulk modulus, and the behavior of the data as a function of temperature seems to be qualitatively correct. And so I now plot the bulk modulus, the shear modulus, and the Young modulus as a function of alpha of this microgel for different cross-linked concentration, and we have reasonable results. So basically that, for example, a stiffer microgel with more crosslinks has higher moduli, that K is greater than G, and all the moduli are monotonically increasing with temperature. So the particle gets more collapse and the moduli increase. So the particle is stiffer. The most interesting result of this part is the Poisson ratio, because we have that at low temperature is with this value that is more or less what is seen experimentally in microgel and hydrogels. And then it increased above the volume phase transition up to tending, it will be eventually tend to the Hounsfield limit of 0.5. But the most interesting thing is that there is a minimum at the volume phase transition that becomes more and more evident as you decrease the cross-linker concentration. And this was actually observed in experiments performed by Hans-Biss group, in which basically they use a very, very large microgel of micron size made by microfluidics, and they use basically an asymmetric capillary. They call it capillary micromechanics, and he was able to simultaneously measure K and G for these huge like 100 micron size microgels. And he observed the onset of this minimum at the volume phase transition. So this is at least tell us that the method works well from the physics point of view. Then we take two microgels, we calculate their effective interaction, that is basically the log of the GOR. And then we use two methods, umbrella sampling to probe so we fix the microgel at given distances and we calculate the probability of finding at a given distance, and we measure the interval of all possible distances, and then we use also Vidom insertion at very low energy strength. And the two methods work very well, and this is for a given alpha, and we were able to do 3 alphas below the volume phase transition, because when you go above, I told you, you have attractive interactions, and then the microgel will stick forever, and we are not able to really probe the probability well enough to have a good effective potential. But for this particular microgel at 3 different alpha, we find that in all cases the potential is repulsive, and the particle shrinks, and so the potential becomes smaller and smaller in terms of the monomer size. And then we are able to test the Hertzen model, because we have from the Hertzen fit, we have the moduli that we have calculated separately, and the only fit parameter is the sigma, that is this effective radius that we also know how it scales with temperature, so we can see whether we get good results. So when we do this exercise, actually, we find that the Hertzen model works at moderate distances. So in the small deformation limit, when you start to make the microgel closer and closer, we have very, very strong deviation. And actually, this translates in the fact that if you go a packing fraction above between 0.5 and 1, you start to see deviation, and above 1, you have a lot of deviation. And so you cannot use the Hertzen model for microgels at very high densities, as people usually do. And so one needs to do a little bit better. So in the remaining 5 minutes, I would like to just give you a hint of what we did also at the interface. And so I call it from 3D to 2D, in the sense that we now put the microgels at the liquid-liquid interface. And it's very interesting. This is also a very promising field in which the microgels, because the idea is that soft colloids can really deform, and so they can maximize the contact with the interface, and so they can be used for a lot of applications, like also for emulsion stabilizer and so on. And it's very interesting to study this also because of their assembly at the interface. So to do this, actually, we have to do it all over. So introducing an explicit solvent. And we use dissipative particle dynamic simulation because this is easily implemented in lumps. And the first thing we did is that we redid everything we did with the implicit solvophobic potential in an explicit solvent with DPD. Just to match basically what we had achieved, so the same form factor, the same swelling curve, and so on, so that we have an identical mapping between the two models, because the implicit model we had tested with experiments, and also because with the explicit solvent, of course, we cannot arrive at 100,000 monomers, but we are fixed to 10,000, 20,000, so on. And then we now put two solvents. with different affinity to the monomers, and we want to see how the microgel deforms at the interface. And the typical configuration that the microgel adopts is called fried egg shape, because basically it flattens completely at the interface and it develops a kind of fried egg thing that is the core due to this core corona structure that of course we can reproduce because we have a core corona structure that produce in the preferred solvent, typically in water. And this is an FAM plot taken by Lusoisa, which illustrates this also in the direction perpendicular to the interface. So to do this, then what we did, once we have our model of the solvent, the microgel in explicit solvent, we try to tune the DPD affinity of the microgel to the solvent. And at the beginning, we tried different couples of affinities. And at the beginning, we thought, okay, the microgel really likes water, so let's put very high affinity and very bad affinity for the oil. But whatever affinity we put for the oil, if the affinity to the water was the best, then basically we would have that the microgel would not absorb. Equally, if we use two large values of A, then we would have something that is basically completely compact. So the good way to model this is to take something in between the swelling curve to have not too much difference between the oil and the water affinity, but a significant one, so that we can basically assemble the microgel at the interface. And in this way, the fried egg shape with the protrusion in oil is recovered. And we tested also this doing several concentric concentration, comparing with the experiments of Lusoisa group. And we could see that basically the deformation that the microgel takes as you decrease the cross linkers becomes larger and the protrusion becomes bigger. And in the oil, you basically have no protrusion here, and then it starts to have a little bit when the core is very, very stiff. So the model works. And the last thing I want to tell you is that, okay, we are interested in the effective interactions. We are interested in the assembly of this microgel. So let's do the same exercise we did before. Let's calculate the effective interaction of two microgel at the interface. And this is the resulting effective potential for 3 cross-linker concentration. And let's compare again to the Hertzian model, that the Hertzian model in 2D is slightly modified. It depends only on the Young modulus and has a logarithmic term. And if you do that, then the surprise that we got is that basically the effective interaction between two microgel at the interface is perfectly Hertzian. And we now, before we were talking about few KT, now we have reached a case in which we are at more 500 KT, and you start also to have core-core interaction, and the Hertzian model works perfectly. So we did also the elastic moduli calculation can be done also in 2D. I don't go into the details, but basically we could see that the Young modulus that we got directly from the Hertzian fit is compatible with the one of the theory. And the nice result that we got is the fact that if you now compare the moduli, so the same microgel, you put it in bulk and at the interface, and you compare the elastic moduli within the plane stress approximation, so assuming that your microgel at the interface is a 2D object with a given small thickness, what we find is that the Young modulus at the interface is more than 1 order of magnitude larger than in the bulk. And not only the Young modulus, but also K and G. So this means that basically the microgels at the interface wants to stretch a lot. So it has these very, very stretched chains that gives a lot of, a much increased stiffness to the microgel. And perhaps this is just that you are always in small deformation limit when you approach to microgel, and this is perhaps why the Hertzian model works so well. So with this, I conclude. I hope I convinced you that we have developed a new assembly protocol of this microgel particle that is able to reproduce key experimental features, both in bulk and at liquid-liquid interface. And in 3D, we need for advanced models in order to be able to capture these intriguing effects that have been seen, for example, here by this beautiful super resolution microscopy experiments from the group of Frank Scheffel. And in 2D, it will be also interesting to see whether really the Hertzian model works, and the Hertzian model predicts re-entrant behavior, interesting assembly, and so it's work in progress. And what we are doing as well, just to give you a hint, we are varying the internal architecture of the network. We are interested at the moment in hollow migrogels, so migrogels that basically are empty inside, that can be synthesized in the lab, and these are the interfaces are really cute. They are completely flat. We're working on a method to calculate the local elasticity rather than just the total elasticity of the particle, so to see if there is a radial dependence due to the fact that it's inhomogeneous. We are working on hydrogels, so instead of confining them in a sphere, we have an infinite network, basically, which is fully disordered. We are looking at the entanglement and so on. And then the thing that we are doing at the moment is really to have many body effects. So to put more than one migrogel, small ones, but we put at least a few of them, like 20, 30, and try to see how they, what they do at high density. With this, I thank the collaborators in Rome that have contributed to many aspects of this work, all the experimental collaborators that we are really lucky to work with, the funding, and most of you, I want to thank you for your kind attention.
Thank you very much, Emanuela. Thank you very much for this very nice talk. Are there any questions from the audience? Some comments? Jose Daniel Munoz, do you have a question?
It was too clear, or maybe not at all.
Yes, no, I think it was too clear. Yes, yes. Okay. Hello? Someone is talking?
Giacomo, can you hear me?
Yes, yes.
Ciao Daniela, ciao Emanuela. I'm sorry I couldn't join from the beginning. So I will ask a very generic questions. I noticed in the last slide that you mentioned microscopic description and experiment, and the question is my usual one. Do you foresee some room for a mesoscale description of the complexity of the system we're dealing with? I don't know whether Andrea Montessori is or Adriana. I think we should talk. If you see some room in that direction, we should really talk. So I would like to have your comment.
Yeah, I think there is plenty of room. I mean, I don't know at which level, but already perhaps maybe not at the entire particle, but for example, in hydrogen and so on, I think there would be room, especially because I mean, we don't take into account hydrodynamics, and we are not able to really simulate the dynamics of this object yet. So I think that in principle, yes, and also, I mean, if we want to capture some hydrodynamic effects, it would be very, very, very interesting. So yes, definitely, it would be worth starting a discussion on this.
Well, actually, we should definitely set up a meeting, but let me tell you quite quickly. I mean, we can, of course, run colloids in complex flows, in binary mixtures, for instance, but our colloids are very simple. They are just spheres. Yeah. So to me, the real question is, as usual, to inject some chemical or biological, maybe specificity into our mesoscale description. And of course, we can do that to a certain extent without losing, computational viability. But in order to inject this specificity, we need to talk to people who know what the specific details which matter are, you see, because we don't, as a matter of fact.
Yeah.
So again, I apologize because I branched in very late, unfortunately. It's a very complicated week for me. But since we are not sitting very far from each other, I would definitely try to set up a meeting very soon. And thank you for being with us today.
Thank you very much, Sauro. Thank you, Emanuela. There is Marisol. Marisol, maybe you should be able to talk now.
Hello.
Hello, yes, we hear you very well.
Hello, Emanuela. Nice talk. I just wanted to ask a little bit about you. You have mentioned that you hybridize your molecular dynamics with dissipative particle dynamics.
Yeah, so basically
you have some type of hydrodynamics as well, or can you say something more about the?
So we use the dissipative particle dynamics to exclude the solvent. So yeah, it's we do a kind of weird dissipative particle dynamics because we don't have a full dissipative particle dynamics, but our microgel is still interacting with the bead spring model. So it's kind of weird. So we use the DPD as a thermostat in a way, yeah, so we have not looked into the hydrodynamic effects at all, basically.
Okay, so it's just okay, I see. So it's just a thermostat. It's not that you have hydrodynamic interactions in the.
Yeah, sure. Okay, just the very last question by Munoz, José Daniel. Which do you think is the cause of the minimum in the Poisson's ratio?
Is the volume phase transition, definitely. And actually, this is something we are working because all the works about hydrogels, they were talking about actually not a volume. Also in the microgel, you have this volume phase transition because this is a finite object, but in hydrogel, people talk about the critical point. With critical fluctuation, let's say. And so we believe that it should be an echo of some, so if there is a critical point, the compressibility should do something, and so the bulk modulus as well. And so there should be a manifestation also in the elastic moduli. And so we think that there is some interesting physics there. And so that is, now we are studying hydrogels as well.
Okay. Thank you very much. I would like you all to thank Emanuela one more time.
Thank you.
For this very nice talk and for joining us at DSFD 2021. Now, I believe that we have time for a very good coffee, and then we can, no, okay, sorry, excuse me. We have the second, the speech by Mauro Sbragaglia. Sorry, I didn't see the schedule very well. Mauro Sbragaglia, my friend and colleague from Tor Vergata University. He will talk about mesoscale investigations of convective heat transfer in concentrated emulsions, finite size effects, and heat avalanches. Mauro does not need any introduction. He is a great scientist. He has a remarkable and very strong background in multi-phase flows with Lattice Boltzmann, and we are very happy that you are here with us today. Can you share your screen, Mauro?
Yeah, I'm sharing. Do you see it, Giacomo?
I see you. I do not see your screen yet.
Let me check once more. Host disabled participants screen sharing.
So, I make you.
I think you have to enable me.
Yes.
Somehow.
Claudia, can you enable him, please?
Yes, sure.
Because I can make him just a spectator. I don't know why.
Okay.
Okay, Mauro, now you are able.
I try it again.
Mm-hmm.
Okay. Let me see. What about now?
Yes, I see your screen. Yes, I see also your presentation.
Do you see my pointer?
Yes, no, the point. Yes, it's red. Yes, Mauro, you have 20 minutes. Please, it is fine for you, 15 minutes, and then 5 minutes for the, for the questions.
Thank you very much.
Thank you very much.
Thank you very much, Giacomo. Thank you very much for the introduction. Good morning, everybody. So I will talk about mesoscale investigations, actually lattice Boltzmann simulations on convective transfer in concentrated emulsions, focusing on finite size droplets effects, and I will just briefly mention in the conclusions issues related to heat avalanches. Let me also mention that this is work done mainly by my previous PhD student Francesca Pelusi, and in collaboration with friends and colleagues from Rome, Roberto Benzi, Andrea Scagliarini, Massimo Bernaschi, and Saur Succi. So the focus of the lecture is on complex fluids in general and the soft materials in particular. Those materials, complex fluids, characterized by a collection of soft objects at the mesoscales dispersed in a continuous phase, Examples come really from everyday life. Think about mayonnaise, that is an oil in water emulsion, or a beard foam, that is a gas in liquid dispersion, or a gel. These kind of soft materials are actually characterized by really a complex mesoscale structure, and they display a variety of complexities, including clustering, aging, and so on and so forth. And importantly, they are characterized by a complex rheology. Complex rheological response, it is complex in comparison to, let's say, Newtonian fluid. Let's say, water, for example, at large scales, and let's try to relate the force that we have to apply to set the fluid in motion to the developed velocity gradient or shear rate. So for a Newtonian fluid, we all know that this is just a linear relationship whose slope is essentially the dynamic viscosity of the fluid. Now, the situation gets much more complicated in presence of a complex mesoscale structure, for example, the one of a model emulsion. So the rheological response gets complicated and depends strongly on the droplet concentration. So for small concentration, the emulsion behaves as a Newtonian fluid with an augmented viscosity, which means that the slope is increasing. And for larger concentration, there are shear thinning effects, meaning that the resulting viscosity becomes a function of the shear rate, and it displays typically larger viscosities at smaller shear rates. At even larger concentration of the droplets, this complex fluid behaves as a yield stress fluid that is displaying a dual nature, mixing together the elastic response of a solid up to some given threshold, above which the fluid flows with a real thinning character. So that's a really complex landscape. And it has been actually characterized in the literature in the last 20, 30 years with plenty of investigations related to the characterization of the mechanical response to external drivings, for example, an imposed shear or stress. There have been characterizations regarding the way this kind of complex fluids flow and the way they start to flow. There have been studies on the emergence of heterogeneous structures, for example, shear bending, and there have been studies on also on confinement effects, focusing on the finite size of the droplets and issues pertaining to non-locality. But much less is known on the way this kind of complex fluid behave in the hydrodynamical framework in terms of convective heat transfer. And that's essentially what stimulated our work. So we will focus on the characterization of heat transfer properties in the paradigmatic setup of the Reibner cell, which means placing our emulsion between two walls, two parallel walls, which are heated from below and cooled from above. The emulsion is subject to buoyancy forces, and if buoyancy forces are suitably large, convection sets in, and essentially there is a transition from conduction to convection. So we would like to investigate the hydrodynamical properties just above this transition. So when there is the emergence of these convective states, and we would like to characterize this kind of transfer properties by changing the emulsion concentration quite systematically. And for numerical reason, let me stress that I will stick to two-dimensional emulsions, and I do not expect that all the conclusions I will draw from my lecture could be greatly impacted by the dimensionality. So a bit, some words regarding the numerical simulations and the kind of lattice Boltzmann that we used. We used a coupled scheme. First of all, a multi-component lattice Boltzmann for two components, say oil and water, basic streaming and relaxation dynamics. So all the relaxation properties are encoded in these relaxation operators that we choose in the BGK framework. And there is a coupled lattice Boltzmann dynamics for another population, G, which is modeling the temperature dynamics. Regarding the non-ideal contributions, we work in the framework of the Pseudo-Potential Lattice Boltzmann approach, sunshine forces. First of all, we introduce a phase segregation between the two components, and this phase segregation is further supplemented by some competing interactions which are instrumental to introduce some positive disjoining pressure at the interfaces here, which is really instrumental to prevent the droplet coalescence in the numerical simulations. So using this methodology, we are able to prepare our emulsion in the desired state with some given number of droplets, and we are able to initiate convection by properly placing another external force, which is essentially representing the buoyancy forces. And this is a crucial force because it's coupling the momentum dynamics with the temperature dynamics. The reference hydrodynamical equations are those of a diffuse interface hydrodynamic system with a pressure tensor, with a bare viscosity. These are buoyancy forces. And for the temperature, we come up with the usual standard advection diffusion equation. And in this hydrodynamical framework, the thermal diffusivity and the bare viscosity are input parameters via the relaxation times of our BGK formulations. That's an illustrative, two illustrative movies of what we can do with this coupled lattice Boltzmann scheme. We can simulate essentially both Newtonian emulsions and non-Newtonian emulsions. So we can change systematically in the Rayleigh-Bénard convection the concentration of the emulsion. So I would like to explore the statistical properties in the hydrodynamical framework resulting from these numerical simulations. But before doing any kind of hydrodynamical characterization on the convection, we need to rheologically characterize the system. So we need to place the emulsion in a cell, we need to apply a force per unit area, which is the stress, we need to measure the resulting velocity gradient, so we need to reconstruct the rheological curves, and we did it at changing the droplet concentration, phi naught, and we actually observe what we expect, starting from Newtonian response, which is becoming an augmented Newtonian response in terms of a viscosity, and then we start observing shear thinning effects. And this is essentially the viscosity resulting extracted from the slope of these plots as a function of the shear rate. And the gray shaded area is essentially highlighting the emergence of these shear thinning properties I was mentioning earlier. Now, let's, we control the rheology. We have fully characterized the rheology. We place the emulsion in the Rayleigh-Bénard cell, and we start convection. So the idea, the first experiment that we performed, and that's the experiment I would like to discuss during the lecture, is an experiment at fixed buoyancy. So we fix these buoyancy forces, and we change the concentration from dilute emulsions to more diluted emulsions, to more concentrated emulsions. So the response of the system is captured, is analyzed via the Nusselt number. That's a dimensionless number that is physically expressing the importance of advection with respect to conduction. And by definition, Nusselt number is equal to 1 when we are in a conductive state. Nusselt number is larger than 1 if there is a contribution of advection to the heat transfer. Now here we see the Nusselt number as a function of time for different emulsion concentrations, starting from a situation where we have no droplets to situations where there is a finite concentration of the droplets. And first of all, we observe that when the concentration of the droplets is increasing, Nusselt is decreasing on average. But also another interesting feature is the emergence of these fluctuations, which would be absent in any kind of single phase fluid. So there are two features. A decrease in the Nusselt number, in the average Nusselt number, and an increase of the fluctuations. I would like to stick to the characterization of the decrease of the average Nusselt number as a function of the droplets concentration. Let me say that it's not surprising that we observe a decrease, because emulsions are more concentrated, which means that they are more viscous, and increasing the viscosity physically means that we are decreasing the propensity towards convection. So we expected a decrease of the average Nusselt number. But we wanted to further characterize this decrease in a more quantitative way. And let's say a logical question would be to, let's say, construct a single phase system, simulate a single phase system, and ask ourselves what would be the correct viscosity of this single phase system that would be needed in order to attain the same heat transfer efficiency. So you may say, okay, you characterize the rheology of the system, you know everything from the point of view of the viscosity characterization as a function of the shear rate. I want to stick to Newtonian emulsions, a situation where the viscosity is just a number independent of the shear rate. So we know the characterizations from the numerical simulations. We can also fit this kind of viscosity plot as a function of the emulsion concentration. So our first guess would be to take this kind of viscosity, place it back in the single phase system, and start the numerical simulations with this global rheology to see what happens. And this is the result. So we have our emulsion with a decrease in the average Nusselt number. We have the single phase system with a global rheology whose Nusselt number is decreasing, but is not matching the one of the emulsion system. So there is a mismatch that may be 10, 15, 20%, but we are unable to quantitatively predict this decrease. We observe a decrease, but we are unable to quantitatively match the one of the emulsions. So we inspected a bit better the system during the convective state in the convective dynamics. And what we observed is that the concentration of the droplets is not homogeneous in space during convection. And this poses an important question on whether we have to choose a local viscosity or not. I mean, we know the viscosity as a function of the concentration, but if the concentration is not constant in space, probably we have to design a single phase system simulation with a local viscosity, where the local viscosity is a function of the local concentration. Now, let me also say that there may be a variety of reasons for this non-homogeneity in space of the concentration. There may be interactions with the walls, hydrodynamical interactions. There may be effective collisions between droplets. There may be a variety of physical ingredients at the core of this heterogeneity. We just take the heterogeneity as an empirical fact. We measure it. So we took this heterogeneity, this heterogeneous concentration, and we constructed the local viscosity, and we repeated the simulations with a single phase system. And the results is displayed here in these blue points, which are now overestimating the results with the emulsion. So the emulsion stays in between two situations, a situation with a single phase system with a local heterogeneous viscosity, and a situation with a single phase system with a global viscosity. So somehow the truth, the quantitative matching, it's obtained via, could be obtained via some situation, some mathematical idea that is somehow lying in between this completely local strategy and this global strategy. So the idea is to coarse grain in space. So take the profile, you introduce a suitable coarse graining length scale, you define a coarse graining concentration, and on top of that, you define a local viscosity, which is further coarse grained. And this is an example of the effect of coarse graining in space, starting from a local situation, which are the blue points. The introduction of coarse graining is smoothing out space heterogeneities up to the point where the coarse graining length scale is so large that you flatten everything. So the situation becomes homogeneous again. So the key— 2
minutes, please, Mauro, thanks.
Yes, the question is to understand what is the value of the right value of coarse graining. It came out that the value of coarse graining properties is obtained by choosing lambda in the order of the mean droplet diameter. That's a result that we obtained for a specific value of the buoyancy forces, and is also found to be robust at changing the buoyancy forces themselves. Let me come briefly to the conclusions. We have studied this convective heat transfer in concentrated emulsions, focusing on the heat transfer efficiency, and in particular the average heat transfer efficiency. And the take-home message is that for Newtonian emulsions, essentially you can't forget about the finite size of the droplets. And if you use a Navier-Stokes equation with local viscosity, you need to coarse grain this local viscosity in space. Otherwise, you are unable to get any quantitative understanding on the system. The same mathematical strategy doesn't work very well for non-Newtonian emulsions, and we believe this is a signature of the emergence of non-locality. So Navier-Stokes with local viscosity must be supplemented with a further equation for the viscosity. And let me also mention that there is a second part on this study regarding the fluctuations which increase at increasing concentrations and which may be traced back to the emergence of what we call the heat avalanches, so collective droplets dynamics at the mesoscales. And thank you very much for your attention. If you have more interest in this study, you can find all the details in this recent publication that came out a few months back in Soft Matter. Thank you very much for your attention.
Thank you very much, Mauro, for this very nice and inspiring talk. Very brilliant. Thank you very much, as always. Are there any questions from the audience? Curiosities, questions, also from the spectators? Let me see if there are some lifted hands. What about, Mauro, the computational burden of this procedure?
Well, let me say that, I mean, we put all this Lattice Boltzmann machinery in a GPU code, and it's mainly work done mainly by Francesca, and the work, this code will be probably in the very next future made available to the community with an open access publication.
Ah, great. Okay. Very interesting. Okay. So
there is a chat, Giacomo. There is a...
Yes, the chat. I don't see any.
No.
I don't see any. This is the previous speaker. Okay. So if there are no other questions, I would like you all to thank Mauro one more time. Thank you very much, Mauro, for joining us and for this very nice presentation. Then we have another presentation by Kulik. Are you there?
Yes, I'm here. Hi.
Okay. Hi, Nadia. The thermal reactive multiphase lattice Boltzmann method. Can you share your screen?
Not yet. Hot disabled.
Let me check. Okay, now you should be.
Not yet.
Well, now you should be able.
Yes.
Okay, yes, okay. Please, you have 15 minutes. At 13 minutes, I will tell you that you have just 2 minutes left. Okay?
Thank you.
Thank you very much. The floor is yours.
My slides, right? Okay. So I'm Nadia Kulik. I'm postdoc in Jens Harting group in Erlangen, Bayern. And today I want to talk about reactive multiphase Lattice Boltzmann model that we developed for electrochemical water conversion. First of all, why we do it? We want to model electrolyzers. They are, this is where we split water. The reaction takes place on anode and cathode separately. Hydrogen ions go through membrane. We want to focus on anode to produce oxygen, but there is no big difference in simulations for this case. And the point is, both on anode and cathode bubbles form, and they drastically affect the catalyst efficiency and the reaction rate. And the question is how to design the reactor to increase the efficiency. What bubbles do to the reaction? There are two ways they can affect the reaction rate. First of all, they remove products from the solution because concentration of reactant inside the bubble can be lower than in the solution, and the reactant diffuses into the bubble. This can increase the reaction, increase the efficiency of the electrode, but they also decrease the available electrode area if they stick to the surface, and they can decrease the efficiency So the question is how to design the electrode and the whole reactor to maximize the efficiency. We can try to solve this problem by simulations. Looking closer, one can look at a single bubble experiment. Here there is a micro electrode with current going through, and the oxygen bubble forms on the electrode, and applying constant current, one can watch the potential at this electrode, and one can see then when the bubble grows, the potential here it's inverted, so the over potential grows higher. Then when the bubble is close to detachment is reducing again, and then when the bubble detaches, the potential goes to the previous value, the cycle begins again. So we can say that dV is a descriptor here of the efficiency. We want to decrease the dV to increase the efficiency of the electrode. In our model, we have multi-component, multi-phase lattice Boltzmann model. We use Penn-Robinson equation of state for the first component, that is water. We use ideal gas equation for the second component, but it's slightly reacting with the first component to tune the solubility. We also change the relaxation time for both components depending on which phase they belong to. And we use D32 Q19 stencil and a standard gentleman's set, BGK, gluoforcing, and succoplating at the surfaces. Little technical detail, for flow-through reactors, we needed constant inlet conditions and open outlet. We chose a convective outlet where we just stream the densities with the flow. For reactive surface, we chose a simple bounce back with recovery. Here we convert a part of the reactant populations into the product at the wall with some reaction rate. This way, the reaction rate depends on the concentration of both reactants and products. We are aware of other models, but this approach proved to be sufficient for our purposes. Let's look at some results. So this is like reproducing that experiment. It's a single bubble on a micro electrode. I will stop the video here. So on the right, you see the concentrations of product, let's say oxygen, in the vicinity of the electrode at different lattice, at different distance from the electrode. It grows as the time goes. And the interesting part happens here when the bubble forms, the concentration drops. So we had oversaturation, and now the bubble absorbs the product, and the concentration decreases down to concentration of the product in the bubble. Then the bubble grows. We have gravity here. It detaches, and the cycle begins again with high oversaturation next to the electrode. Okay, we can look closer at what happens in this experiment. So we calculate the flux of product through the electrode, and we can see the stages of the bubble growth. First, we start with the highest current possible when only water is next to the electrode. Then the oversaturation grows. At B, we have the spike, and then abruptly the bubble forms, and the current grows again with the bubble. the bubble, because there is gravity, the bubble is trying to detach from the electrode, thus leaving some space for water to go in. And then when the bubble detaches, current goes to the initial value and the cycle begins. We can compare it directly to the experiment. In this case, we see all the bubble growth stages, and we don't see the spike at the stage B. We believe that this happens because in experiments there are little bubbles at the electrode staying from the last cycle, and they absorb the oversaturated products, thus not letting the current to drop too much. So the end goal of this work is to simulate a large system, a flow-through tube electrolyzer with inner structure. This is one of the first simulations. And on the lower pictures, you see the photo of such a tubulizer. We are interested in the inner part where the oxygen is produced. And we want to find geometries that help remove the oxygen bubbles from the system efficiently and not let them block the current path. But first, we go to a more simple system. This is also a flow-through reactor, but it's planar channel with electrode at the bottom. You can see the product concentrations growing at the electrode. And on the right, I plot the current with time. So the current drops slightly because the concentration of the product grows, then the bubbles form. And for the upper case, it's a low weighting electrode. The bubbles stay on the surface and block the reactive surface, so the current keeps going down. For the lower one, it's a high weighting electrolyte. The bubbles form and the current goes up because the bubbles absorb the oversaturated reactant product. And you can also see the flow. They will be flying away from the reactor. I don't see. Okay. You can also see that next to the bubble, the concentration of the product is lower than next to the electrode. In this way, we have actually a descriptor of a good reactor. This is the change of the current, the maximum change of the current that we get due to bubbles. One can easily calculate it in simulations and also measure in experiments, so we have a direct comparison. To conclude, we have a reactive multi-component, multi-phase model for electrochemical reactive simulations. The model can reproduce main features of single bubble dynamics, so we are sure we can go further. We can compute current curves and directly compare them to the experiment. As next steps, we want to improve the single bubble simulation, maybe increase the resolution to resolve the smaller bubbles. We want to study the impact of electrode roughness on bubble formation, and finally, optimize the tubular electrolyzer structure. With this, I want to thank my colleagues, Marcelo Sega and Jens Harten, for their helpful discussions, and I'm open for questions.
Thank you very much, Nadia. Thank you very much. Are there any questions from the audience? I think that Jose Daniel Munoz has a question for you. Thanks for the nice work. Could you put defects on the electrode surface to control where the bubble will form?
Sorry, put what?
Defects on the electrode surface.
Yes, we can make some roughness,
Mhm.
or we can change the reaction rate on the surface depending on the position. So not changing the geometry, but like applying catalyst to the surface non-uniformly. That's all possible, yes.
Okay, okay. So, and this has an impact on the formation of bubbles we have seen.
Yes, sure.
Okay, okay, thank you. Other questions, please? There any lifted hand? No, I don't see. Okay, so we have still time for another quick question. Okay, if not, let's thank Nadia one more time.
Thank you.
And please, we can have a coffee break here now. We will meet again at 11 o'clock. So we have a little bit less than half an hour to have a very good coffee. Then we will meet again in the final session of the DSFD 2021. Thank you, Nadia, very much, and thank you all for attending.
This picture shows the accumulation between two sand particles. So in the experiment and of the combustion of the biomass, they really absorbed the liquid bridge. So this question has been answered. The second one is, what is the microstructure of accumulation and its relation with capillary interaction? The third is, what is the influence of agglomeration on the rheological behavior of that suspension? So I will answer these two questions later. So the aim of this project is we want to develop and apply the state-of-art lattice Boltzmann method, which is coupled with the discrete element method to understand agglomeration effect in fluid aspect. So we use DSFD2021 lattice Boltzmann with BGK collision model for the fluid phase, while for the particles are solved by Newton's equation for linear and angular moments. So far, we incorporate the liquid bridge by a capillary force model in the linear motion of the particles. Since we consider the force exerted on the particles center of mass, thus the contribution of the capillary force to the angular motion of the particles is 0 in our case now. So we start to simulate capillary bridge between two static particles. So the particles are fixed, and using a lattice Boltzmann method with a multi-Shenchen model, there's no external forces exerted on the particle, only fluid particle interaction is considered. Then we measure the force and we compare our simulation results with different theoretical models. And we found the model from Villard has high accuracy in comparison with the simulation results. Besides, it is also easy to be implemented into the discrete element method. We also find there is, in some cases, especially when the contact angle is high and also the separation distance between two particles are small, there exist asymmetric liquid bridges. So in this case, all the theoretical models will fail, because in the theoretical models, the capillary force are calculated based on the symmetric liquid bridge. So the interested readers here can refer to our recently published papers. And then we switch to accumulation among the particles. So we use lead particles of dispersed with radius of 3, and the particles are randomly distributed in the system while in a single fluid phase. The capillary force model, as we mentioned, we use a weighted model, and we assume the second fluid uniformly distributed among all the particles. And then all the sides are periodic boundaries in order to have a uniformly distribution of the shear velocity. We use a least Edwards boundary to generate the shear flow. Since we are interested in the rheological behavior of the suspension, so we are interested in the relative suspension, which is measured obtained by measuring the shear stress of the system and also the imposed shear rate. So we first look at the influence of particle concentration. From the figure, we can see that at low capillary interaction and also without capillary interaction, which are the dashed line with circles, we found our measured relative viscosity match quite well with theoretical models from Bachelor and Green. While at higher particle concentration and the lower shear rate, we measured increased relative suspension viscosity due to the reduced shear rate imposed on the interior particles. And with stronger capillary force and the lower shear rate, the particles are tend to form clusters. As due to this, the clusters contribute to the related increase in the suspension viscosity. Then we look at the influence of the substantion. If we influence the substantion, which means we have a higher capillary force. So without, we can see from the movie, without capillary interaction, the particles are homogeneously distributed in the system. However, if we increase the substantion and we observe the clusters, especially at quite high capillary interaction, big clusters are observed, and the clusters tend to be more well separated. If we look at the fraction of particles which have the same cluster size, we found the particle size are increased steadily with increasing capillary interaction. The next one, we want to study the influence of shear rate. So at a low shear rate, there's big clusters and a percolating network is formed in the system. However, if we increase the shear rate, the clusters breaks and particles are distributed more homogeneously in the system. And if we look at the fractions of the particles involved into the same cluster, we found at a lower shear rate, more particles are involved in very large clusters, and at higher shear rates, the clusters break down and particles distribute more homogeneously in the system. We then compare also our measured shear viscosity with experimental data as a function of the dimensionless capillary number under the same conditions of particle concentration, contact angle, and volume ratio from the experiment. And we find that with increased substantion, the viscosity curve moves close to the experimental curve. So the agreement is quite satisfying. However, there are some the agreement qualitative agreement is not satisfactory. So we have two reasons for this. The first is in our simulations, because we assume that the secondary fluids are uniformly distributed among all the particles, which is not the case in the experiment. And the second, we model the particles with a monodispersed. However, in the experiment, the particles are neither spherical or monodispersed. So all of these two reasons could lead to the qualitative agreement between our simulation results with the experimental data. And then we also interested in the influence of the suspending fluid viscosity. So from the movie, we can see at a low viscosity, clusters, big clusters, and more clusters are observed, while at a higher viscosity, the particles are distributed more homogeneously. This is because when at a lower suspending fluid viscosity, the momentum transferred from the fluid to the particle is less efficient. So at higher suspending fluid viscosity, the momentum transfer from the fluid to the particle is higher than that. The clusters breaks down. And then if we look at the suspending viscosity again, we find at a lower suspending fluid viscosity, the relative viscosity of the suspension is higher due to the formation of the clusters. And at a higher suspending fluid viscosity, the relative suspension of the suspension is lower. This brings to the end of my talk. So to make a summary, so we have imposed the capillary force model from Willard into our discrete element simulation method. And we found the rheological behavior of the suspension, such as the relative suspension viscosity are quite sensitive to particle concentration, shear rate, surface tension, and also the suspending fluid viscosity. The particle volume concentration has quite a significant influence on suspension viscosity. The suspension viscosity is high with increasing particle concentration. Under strong capillary interaction and lower shear rates, globular clusters are observed, while at low suspending fluid viscosity, we observe more clusters, which leads to higher relative suspension viscosity. So as an outlook, we found this in fluidized beds, the flow regime is always turbulent. So far, we have not reached that regime. So it would be interesting to study particle clustering on the high Reynolds number, which means we need a turbulent model to consider the turbulence, such as the larger eddy simulation method. Besides, since we made a very simple assumption in a distribution of the secondary fluid, so it is good if we include appropriate liquid transfer model to describe how the secondary fluid is distributed among all the particles to make the model much more accurate. So with this, I would like to thank you for your attention.
Thank you very much, Lee. Thanks very much for this very interesting talk. Are there any questions from the audience?
Yes, I do have a question, Giacomo. I raised my hand.
Yes, please, Mauro.
Okay, thank you very much for the talk. Very nice, Lee. So you mentioned these globular clusters, and as far as I understand, you say it's clusterizing or not, just from the analysis of the movies. So it's just a curiosity. What would be the order parameter that you can use to say it's clusterizing or not?
The globular. So we always if we have quite a low shear rate, or we have stronger capillary interaction, we observe this globular cluster, and the cluster always moves quite slow in the system.
Is there a way to construct a sort of indicator that tells you is clusterizing or not beyond the movie observation?
That's a good question. I'm not very sure about that.
Okay.
How to quantify that?
Okay.
If I may comment on this quickly, sorry. Yes, what we are using, what we're using is basically the size of the cluster itself. So we do the clustering algorithm taking into account which particles are connected to each other within a certain range, and then we just see what is the size of these clusters. We can also see what is the percentage of particles in the system which belongs to some type of clusters, and these are the distribution that you've seen before.
Okay.
If this answered the question, I hope.
Yeah. It's okay.
Okay.
Okay, thanks. The question, please. Are there
I think there is a question from.
I don't see if there are. Okay, maybe yes. Okay.
From the chat. Yes, is from
yes.
Sergio.
First of all, thanks for the talk. Very interesting. I have a question regarding the solid particles. It's not clear to me how are you simulating them and including in the model. Please.
Yes. Okay. Thanks for the question. When I simulate the many particle system, so we use the discrete element method to simulate the particles, and we impose a capillary force model to consider the influence of the liquid bridge. This is the way we consider the liquid bridge effect. So we just impose a force on the particles, an adhesion force. I'm not sure if I answered the question or not.
We do not. Okay. Yes, it's clear to me now. Thanks. Says Sergio Granos. Okay.
Yeah.
So, are there any other questions from the audience? It doesn't seem so. One more time for this very interesting talk. And I would like to and tell me if he is online. Hosseini from the group of Professor Carlin.
Yes.
Okay, Hosseini, yes, now we see you.
Yes, I can see you now.
We see you very well. Please try to share your screen. So, do you have my screen? Yes, we see your screen. Just wait 1 minute because we have to wait for 11:20 to be sharp. Just another bunch of seconds. So it's 11:20 sharp. Ali, the floor is yours. You have 15 minutes. At 30 minutes, I will tell you that you have 2 minutes left. Okay?
Thank you very much. So, as you see from the title, I'll be talking about isothermal multi-phase models, consistent models in the context of the lattice Boltzmann formulation. Maybe a first disclaimer before I start. So I'm placing myself in the entire duration of this presentation in the context of a single component multi-phase flow, as opposed to talks you have seen in this session and previous sessions today. Now, since you've seen a lot of presentations, you're already familiar with the applications of multi-phase flow. So I'm going to spare you the introduction where I tell you about the ubiquity of multi-phase flows in nature and engineering. Instead, I'm going to talk about the different approaches developed to model such flows. First, in the general context of computational fluid dynamics, and then I'm going to go down to the Lattice-Boltzmann level, and we're going to look into the similarities and try to understand how they are related. So typically, if you look at the different formulations for multi-phase flows, they can be categorized and can be seen as pertaining to either one of these two categories, namely sharp interface formulation or diffuse interface formulation. In the context of sharp interface formulation, multi-phase interaction is basically seen as an interface problem and is implemented as sharp jump condition at those interfaces. And if you look at the different subcategories in that category, you have interface tracking approaches where the interface is explicitly tracked via markers such as Lagrangian particles or the grid itself in the context of the ALE. And you also have another class called interface capturing, where, as obvious by the name, the interface is not explicitly tracked, but implicitly reconstructed from continuous fields such as the volume of fluid or the level set where you have a sign distance function. So in those, after the end of every time step from those fields, you can reconstruct sharp interfaces. And these are interesting, but as you have seen in the literature, in the context of Lattice-Boltzmann, I mean, there are very, very few implementations of something equivalent to those formulations. The other formulation, the other approach to modeling multi-phase flows is the diffuse interface models. And this is more regularly seen in the context of Lattice-Boltzmann. Generally, you can divide the diffuse interface formulations as pertaining again to two subcategories. The first one is the so-called multi-fluid methods, where the essence is basically to solve a set, assuming you have two phases, a set of momentum, mass, and energy conservation equation per phase, and then couple them again at the interface via appropriate jump conditions or mass, momentum, and energy exchange equations. And you have different variants of this formulation, like the full consideration of momentum, mass, and energy leads you to 7 equations, and it's known as the Bayer-Nunziato system of equation. And then under certain simplifications, such as infinitely fast relaxation towards equilibrium at the interface between the phases, you can reduce the number of equations to 5, so on and so forth. And then you have another class of formulation, the so-called phase field method, which is quite interesting because contrary to the multi-phase method, which has a diffuse interface, but the diffusivity of the interface is purely numerical and of numerical interest, so there is no physical motivation or background to it. Contrary to the multi-phase in the context of the phase field formulation, for example, for the Cahn-Hilliard equation, as derived and shown by the Cahn-Hilliard, the interface tracking equation that you use actually relies on the thermodynamic concept of minimizing a free energy functional, shown here, that includes two contributions, the bulk free energy and also the excess energy stored at the interface, represented by the gradient of the phase parameter. And typically in the context of the Cahn-Hilliard formulation, people use a double well potential, shown here, which gives you from which you can get the chemical energy, which would give you the final form of the Cahn-Hilliard equation to track the interface. And also the use of the said double well potential, which is symmetrical, imposes a hyperbolic tangent form at the interface, and therefore always symmetrical at the interface. So that's why using the double well potential would eventually miss some thermodynamic properties of the real system, where in reality, as you will see later, the interface is not always symmetrical. And that was also the base of the plenary talk of yesterday around the calculation of the Tolman length. Now, interestingly enough, if you look into it, you can see that so the Cahn-Hilliard formulation was not the first one or the first formulation to change from a sharp interface point of view to a diffuse interface where the excess energy is spread on an interface. This was first proposed and developed, and the corresponding thermodynamics were developed by van der Waals in 1894. And corresponding equations and thermodynamics were derived. And he also had a free energy functional that, as you can see, is very similar to Cahn-Hilliard, except that here the phase indicator is the density. And correspondingly, applying the same, using the same thermodynamic formulation, you can get the corresponding Navier-Stokes equation. Now, Navier-Stokes-Korteweg equation, because in addition to the local pressure, you have contributions, non-local contributions from surface tension that you can see here. Now, this is interesting. This introduction lets me go to my next step, where most of the Lattice-Boltzmann formulation that you see can be related to one of these macroscopic formulations. For instance, not going too much into the detail, the color gradient model developed initially by Rotman and Keller. If you look into the equation, you do the development, you will see that it corresponds roughly to the 4-equation model within the context of the multi-phase method formulation. And under the use of specific recoloring operator, you can also show that you recover a hyperbolic tangent interface, and therefore you can recover the Allen-Kohn formulation for multi-phase flows. Then in the context of Lattice-Boltzmann, you also have free energy models where the double well potential is used to derive the interface tracking algorithm, which is, well, very clearly related to the macroscopic Cahn-Hilliard formulation. And then you have the final class of formulations that's interesting, the pseudo-potential formulation and the free energy method with cubic equations of states. So I'm going to go into the pseudo-potential formulation. It's a very interesting formulation because at first look, you can't really maybe very rapidly see the relationship between the pseudo-potential formulation and any of the macroscopic models that we talked about before. But if you look into it, in the context of pseudo-potential, there is a non-local contribution to the momentum that's formulated like this in its initial version. And this, in turn, at leading order, results in a non-monotonous equation of state, which supports phase segregation. But then, if you do a Taylor-Maclaurin expansion up to order 3 or 5, you're going to see that it also leads to a term like this, which is third order in space. And that's interesting because it looks very much like, if you do the comparison, at least the form looks very much like the Korteweg contribution to the stress tensor, which tells you why the model is able to sustain interfaces and mimic the behavior of a surface tension. And it gets even more interesting if we look at the form and we see that if the pseudo-potential is a linear function of density, then this is exactly the Korteweg stress tensor, with one difference, and the minor difference is you don't have control over the coefficient. But after the development of the model, a lot of people worked on including realistic equations of state in the context of the pseudo-potential formulation. One of them is shown here, and the appropriate reference is here. So if you use these methods to incorporate realistic equations of states, you see that you are changing effectively the form of your surface tension term and making it, well, inconsistent with the Korteweg stress tensor. Now, the whole idea of this work was to take the Lattice-Boltzmann formulation, make it consistent with the van der Waals theory of capillary fluids, and these are the set of equations that we use for the remainder of this presentation. So you have your classical discrete time evolution equations for the equilibrium, product form of the equilibrium, which is equivalent to a 4th order expansion in 2D of Fermat polynomials, or 6th order expansion in 3D. During the entire duration of the simulation, we're going to stick to the van der Waals equation of state. And then we also have appropriate correction terms for the 3rd order tensor and a modified forcing term that guarantees us the recovery of the proper Korteweg stress tensor. Now, on to the results. One of the first things tests usually in multi-phase model development in Lattice-Boltzmann method is the Maxwell reconstruction and coexistence density. So we did the simulation in 2D with a droplet. Simulations were continued until convergence with the convergence criterion shown here for van der Waals. And as you can see, the model is stable and able to capture proper coexistence density up to very, very low temperatures and density ratios up to 10 power 8, 10 power 9. Which is interesting, and in contrast with what was presented in the original formulation of the pseudo-potential model with realistic equations of states. So for the remainder of the simulation, just for the sake of clarity and to show the robustness of the model, we're going to do everything with a density ratio of 1,000 unless specified otherwise. So one of the first test cases to show that the shear stress tensor is consistent is a Poisson flow, so a layered Poisson flow. In the bottom layer, you have a fluid A with a given density and a given viscosity. Top layer, you have fluid B with given density again and viscosity. And this configuration has an analytical solution which can be readily derived and is shown here. Now, if you do the simulation with both a second order equilibrium and the product form or a fourth order equilibrium, you're going to see that at the interface, the second order equilibrium does not guarantee conservation of momentum flux, and therefore you have a pronounced jump, which is very small for density ratio of 10, but if you go to a density ratio of 1,000, well, it becomes more pronounced. But the use of a fourth order expansion or product form allows you to guarantee the continuity of the momentum flux. Now, this by itself is something that's very well known in the context of compressible flow simulation, so it's not very new. And now let's go on to the acoustic properties. In the acoustic properties, so here you can see the results for the speed of sound as obtained from this model, and also the dissipation rate. The speed of sound, as you can see, the model is able to correctly recover the speed of sound in both the gas and the liquid phase, and they agree pretty well with the analytic solution. For the dissipation rate, on the other hand, so the simulation is basically a sine wave of density or pressure, which dissipates over time, and you measure the kinetic energy and you fit it with an exponential function. Now, this is interesting because the correction that we just talked about, which is also routinely used now in compressible flows, is the component that allows you to restore Galilean invariance of dissipation rate of normal modes. And this is clearly shown here. The red ones are the fourth order, the product form equilibrium with no correction, while the blue ones, you have the correction. And as you can see, and as expected, just like compressible flows, it restores consistency to the dissipation rate of the normal mode. Another interesting test case is viscocapillary coupling, and we'll look into that via oscillating drops. Most of you have seen, so oscillating drops were studied by Riley, and he provided analytic solutions for the oscillation of drops via an expansion in the form of Legendre polynomials for an inviscid flow. Now, you've seen the second order perturbation to the system quite a lot in the literature. It's the one shown here. However, you have higher order oscillations that are possible in the context of this theory.
Sorry, you have 2 minutes, please.
Okay, shown here, and you can see the results, and the model is correctly able to capture them. The next step is to look at the dissipation rate. In the literature, there have been articles developing analytic model for the dissipation rate. And again, as you can see from this plot, the model is able to correctly capture the dissipation rate of capillary modes. Now on to dynamic test cases. One of the test cases that's interesting is pancake bouncing. It's interesting because pancake bouncing on a surface with this macroscopic structures reduces the contact time fourfold. So to show the robustness of the model, we did the simulation with density ratio of 1,000 and parameters corresponding to this paper. Here you have screenshots of the simulations, and you can see that the agreements are excellent. And then predictions of the contact times are shown here as obtained from experiments in blue and simulations in red, again predicted correctly, and also the shape of the drop while separating from the surface shown via Q. Again, predictions are excellent in the simulations. Finally, the last test case to show you the robustness of the model, we consider droplet coalescence of two 1 gram mercury droplets. If you look into it, mercury density 13,600 kilograms per meter cube and air 1.2. So this gives you a density ratio of 11,500, which is, well, not quite easy to achieve in the context of classical formulations. So you have there is a paper that has done this experiment, and you have screenshots of the evolution of the droplets over time. And we did the same simulations with the same density ratio. And here you have, again, the surface of the droplets evolving over time as compared to their experimental counterpart. And as you can see, again, the agreement is great. And finally, there is a theory characterizing the evolution of the thickness of what you see here between the two drops, which is usually called the neck. The diagram is shown here. And if you look at the Ohnesorg number of mercury, it falls in the inertial regime. And in the inertial regime, the theory predicts a square root or power 1/2 scaling with time. So we look into the evolution of the thickness from the simulations shown with the gray line. You have the experimental observations from the paper listed here with red dots, and you have the scaling law in blue. And as you can see, the simulations agree very well with the experiments, and plus both of them capture the square root scaling with time. And as you can, so this shows you that restoring the consistency to the model, well, makes the model able to deal with very high density ratios efficiently. And I would take this sentence as the conclusion.
Please, Ali, you should jump to the conclusions, please.
That is the conclusion. That was the conclusion. And thank you again for your attention. And if you have any questions, at your disposal.
Thank you very much for this very nice speech and these very beautiful images. Are there any questions from the audience?
I do have a question, Giacomo.
Please, Mauro, the floor is yours.
Yeah, thank you very much for the talk. Very nice, very interesting. So if I understand correctly, you start from the pseudo-potential force. You first perform a Taylor expansion, and then you do all the analysis to match the desired pressure tensor, right?
So no, the actual approach, so that was the angle for the presentation today. But the actual approach is that the formulation that you see, we can clearly show that it recovers the Boltzmann-Vlasov-Enskog equation under the mean field approximation for the non-local term. And
that's
also,
good, but you start from the force, right?
Yes, this is to point out the inconsistency in the stress tensor of the Shanshan formulation.
Very good, very good, very good. I was wondering whether would that be feasible to start directly from the discrete pressure tensor of the pseudo-potential approach?
Yes, why not?
Did you try it?
No, because the interest here was to develop a consistent model, and in the context of a consistent model, I want to see the behavior of the system in the limit of a very well-resolved interface.
Okay, what is your feeling on that? If you start from the discrete pressure tensor, would that be improving your approach or not?
So if we start with the discrete pressure formulation, obviously this is gonna, that's at least what I think right now, this is gonna help you maybe reduce the number of points needed in your interface. This discrete treatment would take into account the higher order deviations in the expansion and therefore help you maybe deal with these density ratios with less points.
Okay, thank you very much.
Thank you. Other questions, please? Okay, if not, let's thank Ali one more time. Is there any question? I see a lift there. Okay, no, Maurice, it's yours. Okay, so let's thank Ali one more time, please. And we come to the last speaker of this year, this DSFD2021. We top off with a very interesting talk by Silva, Brownian motion of deformable capsules in a fluid. Are you here? Allora, let me see. I cannot see you. Is Silva online?
Yes, he says he has some issues speaking. He says he's there.
Danilo Silva, okay. I can see him, but I cannot hear him.
I am giving him the permission.
Thank you.
Okay, thank you very much. Okay, we see you very well. Yes. Okay.
Okay.
Try to share your screen, please.
Okay.
Okay.
Can you see?
Yes. So we are also on time. So please start with your talk. You have 15 minutes. At 13 minutes, I will tell you that you have just 2 minutes left. Okay.
Thank you very much.
You're very welcome.
For the introduction. So I'm Danilo Silva. I'm a PhD student from the University of Lisbon. And today I'll be talking about the Brownian motion of deformable capsules in the fluid. So first I start off by talking about a little bit about flow of complex matter, which usually deals with the flow of particles suspended in the fluid. For example, the flow of blood flow, as we've seen in various presentations across the week, liquid crystals, colloids, and so on. And usually the behavior of these particles can be given by certain parameters, such as the flexibility, whether the particle is rigid or deformable, activity, if it's passive or active, and shape, if it's isotropic or anisotropic. But today we'll focus primarily on flexibility and activity, and how these two things coupled with hydrodynamics, for example, because the particle is in a fluid, can affect the motion of these particles. Particularly if we look at hydrodynamics and deformation. So if, for example, we have a particle moving in a fluid, it displaces the fluid, and the fluid itself can act back on the particle, leading to different behaviors. So to simulate, first of all, the fluid we want our particle to be in, we use the Lattice Boltzmann method, which the dynamics are very simple, involve a zero streaming collision process with our distribution functions, and with a force term to include external forces acting on the fluid. Also, the Lattice Boltzmann method is very useful for giving an effective fluid viscosity, which depend on the speed of sound of the lattice that we're using. To include external forces acting on the fluid, we can just introduce a density force term to include any external forces acting in this particular fluid. And then it's just a matter of updating our macroscopic variables, such as density and velocity, by summing over our distribution functions. Then, because we want to simulate a particle or a capsule inside of a fluid, we use the immersed boundary coupling in this particular situation, which the immersed structure can be viewed as a parametric surface, and the fluid domain is described in Illyrian coordinates. So in Lattice Boltzmann, we have our Illyrian coordinates, which are fixed points in space, and then the Lagrangian coordinates, which can move in space and depend on time and location. And basically, the change of information between the boundary, the immersed boundary, and the Lattice Boltzmann grid, we use a force distribution, which the force acting on the structure is interpolated onto the fluid from a particular node, and then the fluid velocity from the local fluid velocity around a particular immersed node is interpolated back based on the local fluid velocity. So we can then update our system on this change of information between force distribution and velocity interpolation between the immersed structure and the surrounding fluid. So our algorithm is really simple. So we start our time loop, and we actually use a half time step to calculate our forces and update our system to achieve second order accuracy. So we update our structure at half time step, we evaluated the forces at half time step and spread them, and then from the spreading of the calculation of the forces at half time step, we calculate our fluid velocity for the next time step, and we update our structure based on this scheme right here, and we just repeat until we reach the end of the iterations we want. So also, because we want to study a little bit of flexibility, we add the formable membrane model, which basically consists of a membrane made of nodes and springs, in which the potential energy of the membrane is given by the potential energy of the stretching between the springs, the bending between the springs, and the area of our capsule, of our membrane that encloses. And so we have then a stretching coefficient, Ks, and a bending coefficient, and an area coefficient as well. So in which, for example, for stretching and bending coefficient, we have here our subscript J0, which basically represent our equilibrium position. So Lj0 is our equilibrium length, and theta J0 is basically our equilibrium angle. Here we also introduce a potential energy for the area, so we don't allow the particle to be compressible, so it's incompressible. So we choose a certain value for Ka for it to be incompressible, so that the change in area is very, very small, less than 1%. So with this in mind, we can just quickly verify if everything works fine. And we simulate, for example, a particle settling in a fluid in a particular channel. We discretize our system. We have a certain time step, a certain diameter for our particle, and we choose values of the stretching and bending coefficient, which allow the less deformation as possible. So to approach a more rigid regime as possible. And the settling velocity is basically calculated from the drag coefficient from its Reynolds number. So it's a very Reynolds number. We can calculate our drag coefficient solely based on the Reynolds number, only for Reynolds number very, very smaller than 1. And then we can obtain our settling velocity. And we can see that we are able to recover the motion of this capsule in a fluid. And we can see here, if we plot the velocity against time, we can see our Stokes prediction against the simulation are very close together, with a percentage error of less than 3.5%. Now that we know how to simulate the motion of capsules in a fluid, let's compare them with the motion of point-like particles in the fluid, the motion of these random particles in the fluid can be given by this equation of motion, which we have a friction coefficient due to the particle interacting with the fluid, and a random force, which accounts for the interaction of all the molecules with the particle, and this random force has an average of 0. And we need to take into account also the dissipative time scale, which is the time it takes for the particle itself to diffuse over its radius. And we need to take into account as well the time step, whether the time step is larger than this dissipative time scale, or if it's smaller than this dissipative time scale, in which case we want to resolve fully the hydrodynamics. We need to go for the underdamped equation, where we fully resolve the hydrodynamics at long scales. So first, we look at point particle diffusion with no hydrodynamics. So we simulate 0.1 micrometer point particle at the temperature of 300 Kelvin in water. And we know from the Stokes-Einstein equation, we should have a certain diffusivity, a certain diffusion coefficient from these parameters. If we simulate, then obviously we have a point particle that is smaller than the grid of the lattice Boltzmann. We have to include the hydrodynamic radius, which in this case is the 0.1 micrometer. And then if we measure the mean square displacement and we plot it against time, from the slope of the mean square displacement, we can obtain the diffusion coefficient, which in this case, where we can see we're able to recover very, very close values to the diffusion coefficient expected in the case with no hydrodynamic interactions. Now, for a point particle diffusion with hydrodynamics, then with the friction coefficient, like I mentioned previously in the equation of motion, we can see that we are able to recover, at least at the same order of magnitude, the same diffusion coefficient. However, we can see that there is here inertia plays a much bigger role, where in the previous case, the particle falls tightly, should follow tightly the motion of the streamline of the fluid. In this particular case, no, because we have a massive particle, so inertia takes a role. And we can see that there is a delay before it reaches the diffusive regime, depending on the inertia of the particle. But it's still able to recover at long time scales the same diffusion coefficient as expected, at least of the same order. Now, moving on into the hydrodynamic interactions for a rigid capsule. Now, for a rigid capsule, we do the same thing. The only thing is that we discretize our system now. So we can have a capsule of a 0.1 micrometer size. So a capsule with the same sort of parameters, 300 Kelvin in water. And we see that also, again, we recover diffusion coefficient about the same order of magnitude as the expected given by the diffusion, by the Stokes-Einstein equation. And this behavior of seeing this transition from ballistic to hydrodynamic regime to a diffusive regime has been seen in experiments. So where at very short timescales, we have a diffusive regime, and then we have a hydrodynamic regime, and then finally reaching a diffusive regime. Now, like I mentioned in the beginning as well, since we want to look at flexibility, then we can vary our stretching coefficient and our bending coefficient to see how these parameters affect the diffusion coefficient, or at least the motion of this particle. So now if we simulate again a 0.1 micrometer particle with the same parameters, and we vary now the stretching coefficient for which the ratio between the stretching and the bending coefficient remains the same, and we vary the stretching coefficient, we can see that we measure the diffusion coefficient. We see that it doesn't change much. It's still about the same order as the expected given by the Stokes-Einstein equation. But if we plot the non-dimensionalized version of the mean square displacement against time, where 1 basically indicates the diffusive regime, so it's reached a diffusive regime, and below 1, it's a non-diffusive regime, we see that for more rigid particles, it reaches a diffusive regime faster than for more deformable particles, as we can see here. So for a Ks of 5 times 10 to minus 4 Newton meters, it reaches a diffusion regime faster than its other counterparts for more flexible regimes. So this is quite interesting to observe this transition, that not only hydrodynamics are able to delay the transition from non-diffusive regime to diffusive regime, but flexibility also appears to have a certain role into this delay to diffusive, for a non-diffusive regime to a diffusive regime. So that's the end of my talk. Thank you very much. If you have any questions, please do ask.
Okay, thank you very much for this very nice talk. We have plenty of time for concluding. Are there any questions from the audience? Mauro, do you have I see your hand lifted?
No, that was before.
Before, sorry. Okay, sorry, excuse me.
I have a question,
Please, Marco, thank you very much.
Okay. While it is clear to me that essentially you have used a Verlet algorithm to integrate in time the initial equation of motion without the random term, which is the integrator that you have used for the Langevin equation, which is essentially it's a Langevin equation.
So it's the Verlet algorithm that I used.
Again?
Yes.
But you should also to discretize the integral with the random force, which is not so trivial.
You mean the discretization of the random force?
Exactly. The Wiener process.
Oh, okay. Oh, so for the random force, I basically used a distribution function with zero mean to account for the random force.
Yes, and you extract a number, I think, and multiply for delta. Usually is delta t raised to the power half, and if you use something more accurate like the Dunweg or the Cicotti or there are plenty scheme like the Ekan scheme, you should also extract a second random number in principle and multiply for delta t raised to a power of 3 divided by 2. And in this case, you obtain an integrator which has a strong convergence of 1.5, which in any case less than the Verlet algorithm, which
Okay.
is 2. Okay, but okay.
Thank you.
Prego.
Okay, please, other questions? So let's thank our speaker one more time, and let's wait a few minutes for the final talk for the conclusion of DSFD 2021. Thank you very much. Yes.
Thank you.
A few minutes. Okay, good morning to everybody. This is our last meeting in DSFD 2021. I hope you hear me. I'm Giacomo Falcucci from the University of Rome Tor Vergata, and I am part of the organization committee of this DSFD 2021. Also this year, we were forced to meet in remote through Zoom platform, and we hoped to make a hybrid version this year, but unfortunately due to the COVID pandemics, it was impossible. But I think that our DSFD 2021 was a success. Thank you to you all that attended, with so many of you. We reached 140 attendees and 60 presentations this year, which are quite respectful numbers for our community. And the level of the talks was very high. So I would like to thank you all for these very interesting talks and topics that we covered during this DSFD 2021. We opened with a very interesting and prestigious topic by Professor Giorgio Parisi, one of the greatest physicists in the world. We continued with Professor Koumoutsakos from Harvard, Benedict Dorschner for the plenary talk in the second day, Tim Kruger, Matteo Lulli, Adriano Tribocchi, and Emanuela Zaccarelli today. I would like to thank all these keynote and plenary speakers for joining us and for their very interesting topics. I would like to thank you all, but above all, I would like to thank my comrades in the organization committee, Claudio Buonantonio and Stefano Mastrostefano from the University of Tuscia, who did all the hard work from a computational point of view and set up everything. Marco Lauricella, my friend and colleague from IIC. Andrea Montessori, Adriano Tribocchi, they really made miracles to chair all the sessions with very few advanced in calling them. I would like to thank Stefano Bertini, the rector of University of Tuscia, who hosted us this year and also last year. And he was, as always, great in giving us all in covering all our efforts. So I hope really very much to see you next year. I thank the organization, the scientific committee of the DSFD for being always present and for their support. And above all, I thank you all for being here in such a different period, but for making DSFD 2021 such a great success from a social and also above all a scientific point of view. So thank you really very much. And I hope to see you in DSFD 2021 in person. Let's hope the most important thing is to be able to see each other in person. So thank you very much.
Thank you very much, Giacomo.
See you soon. Thank you very much. And see you soon. Bye-bye.
Bye-bye. Ciao.
Bye.
Ciao a tutti. Bye-bye. See you soon. Ciao Matteo. Ciao a tutti.
Ciao, Giacomo.